Hello students, so far we have discussed the basic concepts of probability and random variables. In the last lecture, we discussed the linear algebra of random variables. Today we will give an outline of random processes. In fact, in statistical signal processing, we model the signal as a random process, and therefore, statistical signal processing is the processing of random processes. We will start with the definition of random process. Random process, that is RP, we will abbreviate it as RP. A random process maps its sample point to a waveform, unlike a random variable which maps a sample point to a point on the real line. Here it will be mapped to a waveform like this. Suppose this sample point is mapped to this waveform. This is the time axis. So, there is a waveform varying with time, and one sample point will be mapped to one of the waveform. More formally, a random process on the sample space S can be defined as an index family of random variables. So, a random process comprises of x s t such that S belongs to the sample space and t belongs to some index set tau. So, tau is an index set and tau usually denotes time. So, essentially it is a function of both S and t. So, it varies with S as well as it varies with t. If we fix the sample point for fixed sample point S naught, x S naught t is a realization of the random process, and it is a deterministic function because we are considering only one S naught. And our practical realizations, whatever we signal we observed, that is modeled as a single realization of a random process. This is an important point. Any observed signal is considered as the realization of a random process. Like in the case of random variable, we omit S. Therefore, x s t is normally denoted by x t. Here is an illustration of random process. This is the sample space. We are showing 3 sample points, and each sample point is mapped to a sample function like this, waveform like this. Okay. Our concern is discrete time random process. A discrete time random process x n is defined at discrete points of time. So, here the index set tau is a subset of z, z is the set of integer. So, on integer points the random variables are defined. Such a discrete time random process is more important for signal processing point of view. Therefore, we will be discussing only discrete time random process. As an example, a sample space waveform is modeled as a discrete time random process. So, a sampled space waveform that we can represent as a random process. Probability structure of a random process. We know that random variable is described by CDF. Similarly, random vector, it is described by joint CDF, and similarly we defined also probability density function, probability mass functions, etc. How to have such characterization for a random process? To describe action, we have to use joint CDF because it is an index family of random variables. So, we have to consider joint CDF only. And this joint CDF we have to consider at different instance of n. Suppose you consider any positive integer k, then x n1 xn2 up to xnk represent k joint random variables, because we are considering the random variable at instant n1, n2 and so on up to nk. So, there are k joint random variables, therefore, they can be characterized by the joint CDF. This is the joint CDF of the random variable xn1, xn2 up to xnk at point small x1, small x2 up to small xk. Now, this CDF must be defined for all k belonging to n, because this index set is an infinite set. So, all possible values of k we have to consider. Similarly, this n1, n2 etc. we can place also anywhere on the time axis. So, this for all nk belonging to tau we have to consider. Therefore, all these considerations make the joint CDF characterization of a random process difficult. So, we have to have some simpler description of a random process. We can define various moments and central moments of a random process. For example, we can define mean of the random process E of xn. Now, this we have to consider at all possible instant of time. So, E of xn is equal to, it will be again a function of n for all instant of time n. Similarly, other moments also we can consider, for example, autocorrelation function. This is denoted by Rx n1 n2. What is this? E of xn1 into xn2. This is the joint expectation of xn1 and xn2. This parameter Rx n1 n2 also we have to consider for all possible values of n1 n2. And autocorrelation function gives the similarity of two random variables at different instant of time, xn1 into xn2, and then you are taking the average value. We can also characterize a random process by autocovariance function. Cx of n1 n2 is equal to E of xn1 minus mu x n1 into xn2 minus mu x n2. So, you subtract the means from the corresponding random variable and then you find the joint expectation, and this we can show that this quantity is equal to Rx of n1 n2 minus mu x n1 into mu x n2. And similarly, we can define different moments, for example, third order moments, fourth order moments, etc. We will give an example, Gaussian random process. The process xn is called Gaussian if for any k belonging to n and any time points n1, n2 up to nk, the random vector given by this column vector with elements xn1, xn2 up to xnk is jointly Gaussian with the joint PDF. This is the PDF. We have already discussed about this PDF. So, PDF is the Gaussian PDF and given by e to the power minus half x minus mu x transpose into Cx inverse of the covariance matrix into x minus mu x, and divided by this normalizing factor root over 2 pi to the power n square root of determinant of Cx. As we know, Cx is the covariance matrix that is given by E of x minus mu x into x minus mu x transpose. Similarly, mu x vector, it is the mean vector and it is the vector comprising of mean of each component random variable. So, that way this jointly Gaussian random process is important for us, and it has comparatively easier description because we have a, for any n or any k we can have this joint PDF. Because the probability structure of the random process is very complex, we have to have some simple assumptions. One such assumption is stationary random process. A random process Xn is called strict sense stationary, that is abbreviated as SSS, if its probability structure is invariant with time. So, whatever probability description is at this point of time, suppose the same probability description will hold for another instant of time, maybe after 1 month. In terms of the joint CDF, we can write that is joint CDF of random variable xn1, xn2 up to xnk at point x1, x2 up to xk. So, joint CDF at these points is same as the joint CDF of the random variable. Now, we will shift the time axis by an amount, integer amount h. So, x of n1 plus h, x of n2 plus h up to x of nk plus h. If we consider this set of random variable instead of this, then also this joint CDF will remain same. So, that means each random variable we are shifting by the same amount. X n1 has become x of n1 plus h, x n2 has become x n2 plus h, and under such condition the CDF at a set of points will remain invariant. This is the strict sense stationarity. Now, to analyze strict sense random process is highly complex. We look for still weaker form of stationarity. So, that is the weak sense stationary random process or wide sense stationary random process. A random process Xn is called a wide sense stationary process WSS, that is if for all h n, n1 and n2, number 1 E of xn is equal to E of xn plus h. So, 2 instant of time E of the average value is same, that means average value must be a constant. Rx of n1 and 2 is same as Rx of n1 plus h, n2 plus h. This is for all h. Now, we can put h is equal to minus n1, then Rx of n1 n2 will be equal to, now this h will be, if we put minus n1, this one will become 0 and here it will become n2 minus n1. So, Rx of n1 and 2 will become Rx of 0 n2 minus n1. So, if we want this condition, then this is equivalent to the statement that Rx of n1 n2 is a function of lag n2 minus n1 only. It does not depend absolutely on n1 and n2. It depends only on the time difference n2 minus n1. So, such a process, therefore, for a wide sense stationary process, the mean E of xn is constant and the autocorrelation function Rx of n1 n2 is a function of n2 minus n1 only. We will give an example of a WSS process, that is a sinusoid with random phase. Consider this is the sinusoid, xn is equal to a cos omega naught n plus phi. N omega naught are deterministic constant. Suppose a is the amplitude and omega naught is the frequency, these are known, only phi is unknown, and phi if we model phi as uniformly distributed random variable, this is the symbol for uniformly distributed random variable and it is uniformly distributed between 0 to 2 pi. So, this phase part is a random quantity which is uniformly distributed between 0 to 2 pi. So, for this we can find out the PDF of this random variable, because this is the random part. So, PDF will be, therefore, since it is uniform, it is 1 by 2 pi for phi lying between 0 and 2 pi and 0 elsewhere. Now, how to find out E of xn? Because It is a function of this random variable phi. Therefore, we can find the expectation of this function of random variable as that is range of the random variable is 0 to 2 pi. Therefore, this is integration 0 to 2 pi of a cos omega naught n plus phi into 1 by 2 pi d phi. And this is a cosine function in a period. Therefore, integration will be equal to 0. So, what we see that mean is constant. Now, let us find out R x of n1 n2. This is equal to E of x n1 x n2, that is by definition, and that is equal to E of a cos omega naught n1 plus phi into a cos omega naught n2 plus phi. Now, there is a product of two cosine terms. We can use the relationship, that is cos of twice cos A cos B is equal to cos of A plus B plus cos of A minus B. So, if we use this identity, then we will have this is equal to A square by 2 into expectation of cos of omega naught n1 plus n2 plus 2 phi. This and this are added, plus cos of this and this are subtracted, cos of omega naught n1 minus n2. So, this part, now this is a cosine function. If we integrate over 0 to 2 pi, you will get 0. So, therefore, expectation of this part is 0, and this part does not involve phi. So, there is it is a constant. Therefore, what we will get A square by 2 into cos of omega naught n1 minus n2. So, what we have seen that this autocorrelation function is a function of the time lag n2 minus n1, and its mean is constant. Therefore, xn is a WSS process. Now, a WSS process is characterized by the autocorrelation function Rx of m. This is a very important quantity for WSS random process, because it is characterized in terms of Rx of m only. So, what is Rx of 0? If we put Rx of 0, by definition it will be E of xn into xn, that is E of x square n, and this is the mean square value. That means, this is the square term, you are taking the average, therefore, this is the mean square value, and this is also interpreted as average power, because this average power E of x square n is the power delivered on 1 ohm resistance, unit resistance. So, that way E of x square n denotes average power. So, to interpretation, this is actually mean square value, and this is also the average power of the random process. And Rx of m is an even function, because what we can write is that E of xn into x of n plus m. This is same as if I interchange the order E of x n plus m into xn. Now, this quantity by definition, this is my Rx of m, and by definition this quantity will be this minus this is the argument. Therefore, this will be Rx of minus m. So, what we get is that autocorrelation function is an even function of m. Then magnitude of Rx of m at any m is less than equal to Rx of 0. So, this we can prove using the Cauchy-Schwarz inequality that we know. So, inner product of xn and x of n plus m, if we take the inner product and then magnitude of that, that will be less than norm of xn into norm of x of n plus m. So, inner product is expectation, magnitude of E of xn into x of n plus m, that will be less than equal to norm of xn is square root of E of x square n, norm of x of n plus m is square root of E of x square n plus m. Therefore, this quantity is autocorrelation function, magnitude of Rx of m is less than equal to square root of Rx 0, this is equal to Rx 0. And similarly, this one is also Rx 0, because this is the product of x of n plus m into x of n plus m. So, there is lag will be 0. So, that way both square root together is Rx of 0. So, what we have seen that magnitude of Rx of m is less than equal to Rx of 0. That means, the autocorrelation function has a maximum at the origin, at m is equal to 0, there is a maximum. So, Rx of m is maximum at m is equal to 0. There are other properties also, we will not discuss them. We can consider also multiple random process, for example, xn and yn. So, if xn and yn are two random processes, then their correlation structure will be given in terms of cross correlation function, and this is by definition R x y n m, that is cross correlation argument is n and m. It is the expectation of E of x n, that is expectation of x n into y n plus m. So, cross correlation R x y at point n m is defined as E of x n into y n plus. So, that way we can define cross correlation function. Here also we want to make some simplistic assumption about the correlation between x n and y n, and we define what is known as the jointly White-Sands stationary random process. Therefore, jointly WSS process x n and y n are characterized by their individual autocorrelation functions, and the cross correlation function R x y n m, that is equal to R x y m. Now, we know that autocorrelation function is even symmetric. Similar to that, there is a symmetry property of R x y m. R x y of m is equal to E of x n into y n plus m. This is by definition. And this now, because these are two real number, I will exchange the order. So, E of y n plus m into x n. Now, definition of cross correlation function, we take the difference of second argument and first argument. So, that way this will be now R y x of minus m. Therefore, R x y of m equal to R y x of minus m. This is the symmetry property of cross correlation function. So, that way if these signals are jointly WSS, then we can characterize them with the help of autocorrelation function and cross correlation function. Frequency domain analysis of a WSS signal. We know that in deterministic signal processing, frequency domain analysis plays an important role. We will see if similar representation is possible for a WSS signal. Recall that a discrete time deterministic signal Gn has the frequency domain representation in terms of discrete time Fourier transform DTFT. So, for example, if Gn is the signal, then its DTFT is given by summation Gn e to the power minus j omega n and going from minus infinity to plus infinity. So, this is the definition of discrete time Fourier transform, and it is denoted by capital G omega. And it is easy to see that G omega is periodic with period 2 pi radian per sample. This unit of omega is radian per sample. So, G omega is periodic, therefore, we can find the inverse by this relationship. Gn is equal to 1 by 2 pi integration minus pi to pi of G omega e to the power j omega n d omega. So, we will integrate over d omega, we will get Gn. Gn and capital G omega form a Fourier transform pair. Now, capital G omega, the Fourier transform exists if this sum exists, that is sum from n is equal to minus infinity to infinity of absolute value of Gn is less than infinity. In other words, Gn is absolutely summable. In that case, G omega exists. And we can also write a simpler relationship, that is instead of mod Gn we can write Gn square. In that case, we will have the condition summation Gn square n going from minus infinity to infinity, that is less than infinity. This expression is the energy of the signal. So, if energy of the signal is finite, then its DTFT exists. So, this is the condition for existence of discrete time Fourier transform of a discrete time signal. But such a frequency domain representation is not possible for a random process, because this condition that the energy of the signal is finite is not valid for a random process. The very notion of stationarity implies that the signal never decays, and therefore its energy will be infinite. But the power spectral density PSD of a WSS process exists. So, let us see what is PSD. First, average power of a discrete time random process Xn is, that is Rx of 0, as we have told earlier, that is equal to E of x square n. PSD Sx omega indicates the contribution of each component frequency omega to the average power. This power spectral density is average power per frequency. So, this is the contribution of each component of frequency omega to the average power. So, that way if we integrate Sx omega over all omega, then we will get the average power. So, integrate E of x square n is equal to integration of Sx omega d omega. Okay, this way we can define Sx omega. Okay. And now, how to define Sx omega? So, Sx omega is equal to limit n tends to infinity 1 by 2n plus 1 into expected value of this quantity. This is the DTFT of Xn, n varying from minus capital N to plus capital N. This is the DTFT of the signal in a window from minus n to plus n. So, we are considering a window from minus n to plus n, and we are taking the DTFT of the signal within this range. Now, for a WSS process, this quantity exists actually, though the Fourier transform does not exist, this quantity exists, expected value of this quantity divided by 2n plus 1. If we take limit n tends to infinity, that will be called as the power spectral density. So, we have defined power spectral density. We will discuss what is known as Wiener-Khinchin theorem, that is the relationship between autocorrelation function and power spectral density. Rx Mn Sx omega form a DTFT pair. So, they are Fourier transform of each other. So, Sx omega is equal to that means this is discrete time Fourier transform Rx of m e to the power minus j omega m summing over m is equal to minus infinity to plus infinity. So, this is the definition of power spectral density. Now, this power spectral density is periodic function of omega, therefore, we can take the inverse DTFT and we get the autocorrelation function by this integration. So, it is 1 by 2 pi into integral minus pi to pi of Sx omega e to the power j omega m d omega. So, that way we can find out the power spectral density, and from power spectral density we can find out the autocorrelation function. From this definition, autocorrelation function is an event function, and since from this definition, power spectrum is a real function. It is a real function, because though DTFT is a complex function, power spectrum is only real function. And since autocorrelation is even function, therefore, this part is even, and since autocorrelation function is also real, therefore, Sx omega also must be even. So, with this argument, Sx omega is a real and even function of omega. Now, it is helpful in signal processing if we have the generalized power spectral density in terms of Z transform. So, that is the Sxz is the Z transform of the autocorrelation sequence. Sxz is summation m going from minus infinity to infinity of Rx m into Z to the power minus m, and we can get back Rx of m using this inversion formula. So, that way Z is a complex number. Now, instead of using e to the power j omega only, we have used Z. We will give one example. Suppose Rx of m is equal to a to the power mod of m, mod of a is less than 1, then only it will become a autocorrelation function. Then PSD, we can apply the formula of power spectral density, that power series expansion. So, we will get Sx of omega is equal to 1 minus a square divided by 1 minus 2a into cos of omega plus a square. This is the power spectral density, and this power spectral density we can convert into generalized PSD by putting, suppose instead of e to the power j omega, we will put that is equal to Z. E to the power minus j omega is equal to Z inverse. So, that if I add both, then cos omega will be Z plus Z inverse divided by 2. So, that way we get this relationship. So, that way we introduced power spectrum and generalized power spectrum. Power spectral density is also called power spectrum, and let us summarize. A random process xt is a mapping from the sample space to a waveform. So, this is one important point. We define discrete time random process xn as an index family of random variables, where the index set tau is a subset of Z. We can take Z as the index set. This Z is the set of integers. Stationarity plays an important role in analyzing a random process. For a strict sense stationary random process, this joint CDF at instant n1, n2 up to nk is same as the joint CDF at instant n1 plus h, n2 plus h up to nk plus h. So, joint CDF is invariant under the translation of the time axis, and this is true for all k, and this is also all placement of h, n1, n2 up to nk. So, that way this is a very complicated expression which we have to apply to test whether a random process is strictly stationary or not. So, to relax this condition, we defined a random process xn is white sense stationary if E of xn is constant, and Rx of m, that is the autocorrelation function, that is by definition E of xn into x of n plus m, and it is a function of lag m only. So, it does not depend on n, it depends on only on the time difference m. Then we call it as a WSS random process. We give one example of WSS random process. Also, a discrete time WSS random process xn is characterized in terms of autocorrelation function Rx of m, because mean is constant anyway, therefore, this autocorrelation function Rx of m characterize a discrete time random process. Rx of m is an even function of m with maximum at m is equal to 0. So, that we have proved that Rx of m has a maximum at m is equal to 0. that we proved using Cauchy-Schwarz inequality. Then this is the Wiener-Khinchin theorem for discrete time random process, that autocorrelation function and power spectral density form a DTFT pair, that is Sx of omega is the discrete time Fourier transform of the RxM sequence. Similarly, RxM can be found from the PSD by this expression. And in signal processing, the generalized PSD is useful. So, it is given by the Z transform of the RxM sequence, and when we put Z is equal to e to the power j omega, we get the power spectrum, that is Sx of omega we can get. We also gave one example to illustrate how Sx of Z can be obtained from Sx of omega. In the next lecture, we will discuss the output of a linear system when a stationary WSS signal is applied as an input. Thank you.